Hello everyone and welcome to Chapter 5 on congruent triangles. In today's lesson we are focusing on Section 5.1, angles of triangles, and we're going to divide this into two different sections. The first one is probably a lot of review. We're going to start with classifying triangles, and the first way we can classify them is by their side lengths. You're familiar with a scalene triangle, which has no sides that are the same length, so there's no congruent sides. And then isosceles triangle has at least two congruent sides. And then we have the equilateral triangle where we have all three sides are congruent. The second way to classify a triangle is by the angle measure. We have learned in the past about acute angles, obtuse angles, and right angles. We know acute angles are any angle that's less than 90 degrees. Obtuse is greater than 90 degrees. And when your angle measure equals 90 degrees, it's a right angle. Putting this into perspective for triangles, when you have three angles that are less than 90 degrees, it's called an acute triangle. When you have that one angle measure that is 90, it's called a right triangle. When we have one angle that is obtuse or greater than 90, it's called an obtuse triangle. And you can only have one obtuse angle in a triangle. You cannot have two. You can have two acute angles, but only one obtuse. And then we have equal angular triangle, and that is where all three angles are the exact same measure. And so these will all end up being 60 degrees, which we'll talk about later in this chapter. Let's do an example where we are going to classify and name some triangles. In this example, they are asking us to classify each triangle shape by its sides and angles. I'm going to give my answers with the side name first and then the angle name second, because that's just how it's asked in the directions here. So looking at picture A, we have this triangle here, and we've got 3 feet and 3 feet. So we've definitely got an isosceles triangle because an isosceles triangle has two congruent sides. So isosceles, it's actually one of my favorite words to spell. And then look at the angle measures. We have two acute angles and one obtuse angle. So this angle, since it's obtuse, that overwrites everything else, and we're going to call this an obtuse triangle. Picture B, we have side length A, side length B, side length C. All of these are going to be different lengths. So this is a scalene triangle, and it looks like we have one obtuse angle in this triangle here, so it's an obtuse scalene. And we will write obtuse second because, again, that's the way it's listed in the directions. Over here, we have side length E, and side length F. So we have two E measures, therefore we have something that's isosceles, or not something, it's actually a triangle. And we have this indication in the corner here, that box that indicates that it's a right angle. So this is 90 degrees, so it's a right triangle. We are going to do another example, and this one we actually need to apply the distance formula and the slope formula in order to answer it. It wants us to classify triangle ABC by its sides and then determine whether it is a right triangle. First thing we want to do is figure out how long each side length is for this triangle. And in order to do that, we are going to apply the distance formula. If you recall, the distance formula is the square root of x2 minus x1, that quantity squared, plus y2 minus y1, that quantity squared. And you take the square root of the whole thing. So what we are going to do is first figure out this side length AB. And coordinate point A is 0, 3, coordinate point B is 7, 1. I'll call this my x1, y1, x2, y2, because the important thing with the distance formula is to be consistent with what we're calling point 1 and point 2. applying the formula, so we have distance of AB, we're going to take the square root of the change in our x, 7 minus 0 squared, plus change in y, or 1 minus 3 squared, and we have to take the square root of that whole thing. Doing this subtraction, 7 minus 0 is 7, that quantity is squared, plus 1 minus 3 gives us negative 2, that quantity is squared. So we have square root of 49 plus 4, or the square root of 53. Next, let's look at side length BC. So I'm going to write out my coordinate points again, 7, 1 for B. C is 1, negative 1, indicate x1, y1, x2, y2. Find the distance of BC by taking the square root of the difference in your x's, 1 minus 7 squared, plus the difference in the y's, which is negative 1 minus 1 squared. Subtract, we get negative 6 squared plus negative 2 squared. Negative 6 squared is 36, and negative 2 squared is 4, so we end up with the square root of 40. I'm not going to worry about simplifying this right now. I just need to know if the side lengths are the same or if they are not, because that helps me identify what type of triangle we have here. We've looked at AB and BC, so now let's look at side length AC. Coordinate point for A is 0, 3, C, 1, negative 1, x1, y1, x2, y2. Distance of AC is the square root of 1 minus 0 squared plus negative 1 minus 3 squared. We get 1 squared plus negative 4 squared. 1 squared is 1, negative 4 squared is 16, 1 plus 16 is 17, so we have the square root of 17. Comparing these three side lengths, and we can see none of them are the same. So that means we are dealing with a scalene triangle. Now we need to figure out if it's a right triangle. So in order to figure out if it's a right triangle, we need to look at the slopes of the lines. You can either create slope triangles, or you can actually calculate using slope is your change in y over change in x, or y2 minus y1 over x2 minus x1. I'm actually going to just work with the slope triangles. Let me move this up and see if I can fit this all on this screen. Let's work with the slope of triangle for the coordinate points A and B. So we have this rise and run. So the slope AB, if we look at the rise, we're going up 2, and then our run is left 1, 2, 3, 4, 5, 6, 7. So up 2, left 7 gives us a negative 2/7 for the slope of AB. The slope of BC is in here, and it's green, and we are going down 2, left 1, 2, 3, 4, 5, 6. So down 2 and left 6. Negative divided by negative gives us positive, which is good because we have that positive slope. And if we simplify it down, we get 1/3. The last slope we have to look at is AC. Looking at AC and creating that slope triangle, we have a rise of going down 1, 2, 3, 4, and a run to the right of 1. So down 4 to the right 1 gives us a slope of negative 4. So looking at these three slopes, are any of them opposite reciprocals? The answer to that is no. So they're not opposite reciprocals, therefore they are not right triangles, because you would get opposite reciprocals to get that 90-degree angle. So not right. Not a right triangle. So that would be our final answer. So in this section, we reintroduced how to classify triangles by their side lengths and angle measures, and we reintroduced the distance formula so that we could calculate the side lengths of a triangle and then calculate the slopes to figure out what classification we could use to describe a figure that's on a plane. That concludes today's lesson for the first half of section 5.1. Please join me again tomorrow for the second half of 5.1. Thanks for listening.